Hello everyone, and thank you for joining us today. The topic of today's webinar are phase change materials, a versatile and broad group of materials applicable in almost any industry you can think of. If you are wondering how these materials are affecting your industry right now, and even more so in the short future, this is definitely the right webinar for you. The presentation will run for about 35 minutes and will be followed by an open question and answer section. During the presentation, please type your questions in the chat panel so we would include them in the section. If you have any technical problems during the presentation, please report them via the chat tool or send them directly to webinar@prescouter.com. My name is Maria Jovic and I will be your webinar host for today. I'm a lead scientist and project manager here at Prescouter. My background is in chemical engineering and chemistry. I obtained my PhD in 2014 from Swiss Federal Institute of Technology, also known as ETH Zurich. It is my pleasure to be here today and walk you through the presentation we have prepared. We would also like to know more about you, so please tell us about yourself by clicking in the poll that you will see in a moment. We will leave the poll open for about 15 seconds. Okay, you still have 5, 4, 3, 2, 1, and thank you for participating. In the follow-up email that you will receive after the webinar, we will be sharing this information with you as well. Today's presentation is based on the topics that are covered in more detail in the full report compiled by Prescouter scientists, including myself. In addition to that, the report also includes exclusive interviews with industry experts. If you're interested in obtaining the full electronic version of the report, please email us at webinar@prescouter.com. To all webinar attendees, we offer a special discount on the accompanying report at the end of this presentation. Here you can see our agenda for today. Before we dive in the fascinating world of phase change materials, I would like to give you an overview of the Prescouter process. Then we will be defining phase change materials and their market share. Subsequently, we will be talking about emerging applications across different industries, and we would conclude with some common misconceptions. And finally, we will have time for questions. Again, you can type them into the chat box throughout the presentation, and we'll try to answer as many as we can at the end. So we're going to start with a brief introduction about Prescouter. Helping companies innovate is at the core of Prescouter's mission. In the realm of corporate innovation, companies are constantly on the forefront of solving challenging problems and incorporating new technologies. Prescouter helps companies like yours by providing answers to the most pressing questions, helping solve your innovation goals, and reducing your tactical work, allowing you to focus on strategy. To date, we have helped over 250 clients like Coca-Cola and Clorox, for example. We do this by providing analysis and insights to understand emerging market opportunities and identifying disruptive technologies, just like the ones we will be presenting today. To give you an example of how Prescouter process works, it is as simple as 1, 2, and 3. First, you start with your question or something you would like to learn more about. Here we discuss criteria for the people, organizations, or technologies you want Prescouter to research. Then for the second step, Prescouter assembles a team of scholars from our network. The scholars are recruited from leading research institutions worldwide and are all under non-disclosure agreements. They use the combination of their own human intelligence network as well as proprietary software developed at PreScouter to answer your query. With a few short meetings with PreScouter's team and through interview and analysis of the information, you receive a deliverable that reflects your innovation needs. On average, our clients find that the report contains between 75 and 80% of information that is new and relevant for them, and that allows them to perform informed decisions and, more importantly, take action. Now, we would like to know, what is the greatest roadblock to innovating at your company? Please select one or few from the ones that you will see listed right now. As before, we will leave the poll open for 15 seconds. And we'll close the poll in 5, 4, 3, 2, 1. And thank you for sharing this information with us. If you have any questions regarding how the PreScouter process operates, please feel free to contact me at webinar@prescouter.com. Now I would like to introduce you to the scholar team that was working on preparing this webinar. Two of them, Veronica and Kyle, will be our presenters today. Veronica, would you like to introduce yourself?
Yes, sure. Hi, I'm Veronica Huang. I am a scientist in molecular and cell biology. I got my degree, PhD degree from Boston College, and went for postdoctoral training at UC Berkeley, studying an infectious disease pathogen. I am very happy to be here with you today and sharing the exciting technologies in phase change material.
Thanks, Veronica. Kyle, you're next.
Sure. Thank you, Maria. Hi, everyone. My name is Kyle Gracie. I'm a PhD candidate in the Engineering and Public Policy Department at Carnegie Mellon University. I've been working for PreScouter for about 2 years now, and I'm very excited to share with you today the wide range of industries that can benefit from phase change materials.
Great. Thanks, Kyle. So I believe now we are all set to dive in the story of phase change materials. Our first presenter for today will be Kyle.
Great, thank you. So let's get started. So a phase change material, which we will abbreviate throughout this presentation as PCM, is really any substance that stores or releases a lot of heat as it changes phases. And let's take a quick poll on this. Have you ever used a phase change material before? So again, we'll give you about 15 seconds to answer this poll. And we'll close this in 5, 4, 3, 2, 1. Okay. Good. Good to see that we have a range of experiences here. Whether you're aware of it or not, you probably have some experience with PCMs. So some examples that you might already be familiar with include a bucket of ice. So the ice absorbs a lot of heat from the air and the drinks as it slowly changes phase to liquid water. Now this keeps the drinks cool much longer than if they were just exposed to the air. And on the right on the slide, you can see an equivalent example for producing heat, which is a hand warmer. It contains a saturated sodium acetate solution. That solution holds a large amount of energy, which is released as heat in the process of the solution crystallizing to a solid. Now, these kinds of solid-liquid PCMs are the most popular for commercial and industrial use because their volume doesn't change much during the phase transition. The rest of this webinar will be exploring a new generation of PCMs in diverse applications such as information technology, biomedicine, and object tracking. Now, the market for PCMs is modest, but growing. From 2014 to 2020, it's expected to grow from US 563 million to 1.5 billion. The largest markets today are number 1, Europe, number 2, North America, and number 3, Asia Pacific. The largest industries driving this growth include construction, heating, ventilating, and air conditioning, textiles, electronics, and logistics. Major factors that are driving this growth include new environmental regulations, corporate cost reduction targets achieved through greater energy conservation, consumer preference for biodegradable materials, and rapid urbanization in developing countries. The research response to this market has been tremendous. Since 2010 alone, there have been 1.1 million journal articles published and 27,000 patents filed, all related to PCMs. So let's talk a little bit about PCM technology. The micro-encapsulation is a special way of preparing PCMs. Even solid liquid PCMs change volume somewhat when they change shape, making practical applications more difficult because the objects are changing shape. One solution is to make many tiny particles or droplets of the PCM and enclose each one in a shell made of polymers or inorganic materials. The shells remain solid and thus the same size when the PCMs change phase. The example on the left here shows an organic micro-PCM made up of a core PCM, in this case N-octadecane, surrounded by an emulsifier. The emulsifier is combined with a melamine formaldehyde prepolymer to form a copolymer shell. The second example on the right is a commercial example, drywall embedded with micronal, which is made by BASF. The micro-PCMs in this case act as insulation in the drywall to reduce the need for building heating and cooling. Now, in addition to micro-PCMs, macro-encapsulated PCMs are like micro but larger, usually greater than 1 millimeter in diameter. They have greater thermal conductivity than conventional PCMs. Because they transfer heat in and out of the PCM faster in this configuration, they are particularly useful for rapidly storing and then releasing the energy generated by some power sources, such as concentrated solar thermal, geothermal, and industrial waste heat. These plants require heat storage up to 500 degrees Celsius, whereas a conventional PCM can typically only handle up to 120 degrees Celsius. Currently, however, macro PCM technology is mostly at the research and laboratory stages of technology readiness. The current research focus is figuring out what materials will make the optimum shells. Looking at industries, the textile industry presents an exciting area for PCM applications. Now here, the goal is improving the comfort of clothing and bedding by better managing heat, keeping out very high or very low temperatures. Now this is shown in the image on the left, where the PCMs absorb the heat from the sun during the day and prevent it from reaching the wearer, while in cold conditions they slow the loss of heat from the body. These applications have their origins with NASA in the 1980s, where here the challenge was really life or death. Astronauts had to be protected from the extreme temperature fluctuations of space. Major challenges for PCM-laden textiles today are keeping the weight of the textile down, since PCMs add bulk, and making sure that the textiles don't catch fire if exposed to flame, since flammable substances like paraffin are a low-cost PCM. A more serious version of this application is in helping people control their core body temperature. The safe range for core body temperature is about 36.1 to 37.2 degrees Celsius. Now, like with the astronaut exposed to space, anything that takes this temperature outside of this range could be life-threatening. On the left, the Embrace is an infant incubator designed for premature babies. It's lined with PCMs that help to keep the baby warm, and this is because premature babies often lack the body fat needed to retain heat, exposing them to hypothermia even at room temperature. The use of low-cost PCMs allows the Embrace to cost just $25, which is less than 1% of the cost of a conventional incubator. This makes it cheap enough to use in many developing countries. On the right, cooling vests like the kind shown here by Glacier Tech help to keep wearers cool even in temperatures as high as 40 degrees Celsius. The vests are first charged by cooling them to low temperatures, and then keep the wearer cool for hours by absorbing external heat. Recharging can take only minutes. The vests weigh only 3 to 5 pounds and cost about $100 to $200. Now, as described in more detail if you purchase the full report, thermal battery management is another emerging application. Overheating is a major challenge in the electronics and hybrid electric vehicle industries because overheating reduces battery power output and can even cause the batteries to catch fire. Surrounding the batteries with a matrix, often made of graphite, embedded with PCMs, can control this heat release. This extends battery life in addition to reducing power loss and fires. The graphite PCM matrix might also be able to act as a shock absorber and/or structural support in hybrid and electric vehicles, which could better protect batteries in a crash or even reduce the overall vehicle weight. Today, however, the high weight and cost of PCMs themselves for vehicle applications is still a major hurdle. In another avenue, police, criminologists, and forensics experts are also looking at PCMs, in this case to help track and identify illegal substances. By placing miniature barcodes on substances that are otherwise hard to assign a unique label to, they may be able to track individual bullets, explosive powders used in bombs, and counterfeit money that lack labeled inks found in real bills. The labeling and detection process works as follows. First, a homogeneous mixture of PCMs, each PCM having a different melting point, is added to the substance to be tracked. Once it's time to read the material, a sample of the material is heated to a series of melting temperatures, and the investigator uses spectroscopy to see what, if anything, melts at each temperature. The combined set of peaks from each combination of PCMs represents a unique identifier which can be read like a serial number or barcode, as shown in the image. It only takes 50 PCMs, each with a unique melting point, to provide enough numbers for most barcoding applications. In a similar manner, PCMs can also help to read biomarkers for diseases like cancers, cardiovascular failure, and autism. Nanoparticle PCMs are attached to ligands that can bind specific biomarkers, such as proteins, that are present with certain diseases. The ligand PCM is incubated in a body fluid to be tested. A solid substrate that can bind the ligand PCMs is then added to the fluid to recapture the ligand PCMs that have attached to biomarkers. The substrate is then withdrawn from the fluid, the PCMs are washed from the substrate, and then they're read using the same barcoding technique that we just talked about of observing different melting points. The advantages of this technique include the ability to detect and track multiple biomarkers at once, a high sensitivity and adjustable detection range by using nanoparticles of various sizes, and minimal sample preparation since the biomarkers are detected right in the bodily fluid. And now I'm going to turn it over to Veronica to talk about even more applications of PCM.
Thanks, Kyle. I'll start by talking about some drug delivery application of PCMs. PCMs can also be used in drug delivery, specifically microencapsulated drugs. Microencapsulation is used to help ensure drugs are delivered specifically to their targets without degradation within the body. The theory is, once the encapsulated drugs are delivered to their targets, the PCMs are stimulated to change phase and thus release the drugs. In the example shown in this slide, a PCM based on modified graphene oxide is made into a nano chocolate waffle, according to the actual words of the researchers. which was used to encapsulate a chemotherapy drug, DOX. This drug was released by exciting the waffle with an infrared laser. This technology can be used in the future to release chemotherapy drugs only at tumors, thus mitigating some of their toxicities and side effects. In the pre-Scouter report, we have another example of microencapsulation method where the rate of drug release is controlled by temperature. We've talked a lot about PCMs undergoing phase changes, but PCMs can also be created where the phase change happens between two different solid forms. For instance, between a semi-crystalline and the solid forms as seen in this slide. This is an example of a class of PCMs called solid-solid phase change materials, or SSPCMs. During the phase change, the materials can shift their arrangement of their molecules and therefore resulting property changes. For instance, the conductivity of a material may greatly change when it transitions from a crystalline solid to an amorphous solid. And we'll talk about some more application where this can be used. Solid-solid PCMs were used by researchers at Massachusetts Maritime Academy as a de-icing coating on communication equipment. Removing ice from communication equipment is surprisingly not a very technical process. In fact, it's a lot like removing ice from the windshield of your car. It either requires the use of toxic materials like antifreeze or the mechanical removal of ice, which is a polite way of saying hit the communication equipment with a bat until the ice falls off. As an alternative to that process, the researchers at Maritime Academy developed a solid-solid PCM coating that expanded at the freezing point of water. When ice formed on the surface of the communication equipment coated by this solid-solid PCM, the coating expanded and thereby disrupted the ice just so it caused it to fall off the communication equipment. The researchers are optimistic that this process will be used as an ice-phobic coating for maritime communication equipment. The pre-Scouter report on PCMs also covers some other applications of this solid-solid PCM. Another type of solid-solid PCM materials are used for solids that can maintain a certain hardness, allow for deformations, but also have the capacity to return to their original shape. These materials are referred to as shape memory alloys, or SMAs. One example of such material are alloys used in the actuators that adjust your car seat. Future applications of SMAs include life-saving technologies like the stents used in heart surgery, which could greatly benefit from being able to remember their shape. Other applications include high-tech, high-end consumer products, such as the Nicklaus brand golf clubs. The golf club contains SMA, which helps golfers put more spin in the ball. The alloy used here was originally designed for the use in a space station by NASA, and is a great example of the far-reaching and the diverse applications of PCMs. PCMs can also be used to store data. In electronic memory, a special type of PCMs could undergo a phase transition when exposed to an electrical charge. These type of PCMs are called thermoelectrical phase change materials. If you've ever used a rewritable CD, you've had your experience with them. Researchers believe that these materials are useful in creating a much faster type of non-volatile computer memory, and also a potential replacement to the existing flash memory, which could lead to a much faster and more powerful consumer electronics. Very recently, Scientists at IBM Research have demonstrated reliable storage of 3 bits of data per cell using PCM. According to Dr. Harris Posides, manager of non-volatile memory research at IBM, phase-change material is the first instantiation of universal memory with the properties of both DRAM and flash, thereby answering one of the grand challenges of the industry. In addition to this, researchers are investigating the use of thermoelectrical PCMs in making an artificial brain. As detailed in the Pre-Scouter report, these researchers believe thermoelectrical PCMs can be used to make a neuromorphic computer that can literally mimic a human brain. This brings a very new meaning to the idea of artificial intelligence, and it's all enabled by PCMs. We've talked a lot about hot topics. Let's move on to some cooler applications. Specifically, there are types of PCM that can help keep things cold. This effect is the result of what are called magnetocaloric materials. PCMs can change the order of the electron spin when exposed to a magnetic field. As a result of this change in the order of spin, the temperature of these materials changes. This is analogous to a gas compression expansion cycle, as seen in the diagram on this slide. While PCMs are still in an emerging area of research, several companies are developing commercial cooling systems based upon these materials. The Pre-Scouter details these technologies and also includes an interview with the CEO of Cambridge. It is a British company developing energy-efficient and gas-free magnetic cooling. Next, people sometimes have some misconceptions about phase-change materials, and now I'd like to take a quick poll to hear about your opinions about phase-change materials. We're going to close the poll in 3, 2, 1 second. Thank you for your participation. Now I'll share with you some of the common misconceptions about PCM, and hopefully with this presentation will help you clear some of those up. The first misconception is that some people would think PCMs as all advanced high-tech materials. In fact, for a material to be a phase-change material, it only needs to release or absorb energy upon undergoing a phase change. Different materials do so to different extents. In fact, an ice cube is a typical example of PCMs, which humans have used for centuries to keep stuff cold. While describing this phenomena can be technical, there is nothing intrinsically high-tech about PCMs. Another misconception about PCM is that they are all expensive. This is partially because with any emerging technology, cost concerns are raised when considering replacing existing technology. While some of this material may be currently expensive, they have the potential to greatly improve energy efficiency and therefore lower costs in other ways. In key areas such as temperature regulation of the buildings. For example, in the US, energy price can be up to 50% lower during low usage periods of the day. And PCMs can be used to store energy as heat during low-cost time of the day and release such energy during times of the day when the energy is more expensive. Alternatively, PCMs can be paired with solar panels. to further help you reduce dependence on conventional sources of electricity. One last misconception about PCM is that they're only useful in the energy sector. Today, we've talked about examples of PCMs being used in golf clubs, space stations, cell phones, pharmaceuticals, medical devices, and keeping people hot and keeping food cold, together with a variety of other areas. I hope you will all agree that PCMs cannot be simply pigeonholed as only important to energy applications. Now I'm going to return the control to our host, Maria, who will continue with this presentation.
Thanks a lot, Veronica and Kyle, for guiding us through some really exciting developments regarding phase change materials. So while we have provided a very broad overview of the applications of PCMs today, it should be noted that none of us are doing the hard work of developing or commercializing PCMs. However, Pre-Scouter scholars have talked to the people who are. The Pre-Scouter report on PCMs contains in-depth interviews with several experts in this field, who are highlighted here, covering a range of topics from technical difficulties to steps towards commercialization. If you would like to learn more about phase change materials, please contact us for obtaining the full report. We will be sending out an email with this information along with the survey following this webinar. We hope that you enjoyed the presentation today. Now I would like to open the floor for your questions. And we have received quite some of them, both via chat and quite some offline, in fact. So I will start first with a relatively general question. And this is, what are some well-known companies that are marketing PCMs? Kyle, would you like to take this one?
Sure. There's a very long list of companies, but it includes, of course, BASF, which we talked about earlier in the presentation. Also, Honeywell is making solar components for solar panels that are designed to use PCMs to function better in high heat environments. And also DuPont is also making insulated wall panels, somewhat similar to what BASF is doing. But again, it's really many, many numbers of companies across a wide range of industries.
Great, thanks, Kyle. And actually, continuing with this, as you mentioned, that many PCMs are used together with thermal insulating materials or as thermal insulating materials. There was a question of what are the advantages of phase change materials over the standard thermal insulating materials. Veronica, would you like to answer this one?
Yeah, sure. The main advantage of PCM, I think, is its ability to store large amounts of latent energy. The thermal conductivity of PCM can be more than 1 magnitude higher than typical thermal insulating materials. Also, PCM will mainly play the role in a dynamic terms, whereas the insulating material will influence in a steady state. In other words, PCM can store and release heat, whereas insulating material works by reducing the heat transfer. So these are the two aspects where PCM shows distinctive materials.
Okay, yep, thanks for explaining this one, Veronica. And I guess we will continue in a similar way. There was another question that was connected with the construction and housing industry. And the question was about what is the current status of phase change materials in this industry. And I guess I can take this one, for example. So the major application of PCM market today in building components, as we mentioned in the presentation as well. So it does account for around 20% of the market share in terms of volume. And the growth of this market in general will be in demand of phase change materials for these industries. Companies like we mentioned, BASF and DuPont, they do have their products, and they're based both on micro they're actually mainly based on micro-encapsulated paraffin composites. And today, the phase change materials are so widespread in industry that you can really find them incorporated almost anywhere. So in building, sealing, the application can be both as a passive storage systems as well as in active storage systems, like for instance floor heating or sealing boards. Okay, so I guess now we can go to maybe a slightly different topic. There was one question regarding textiles, and this one was about like how do you get phase change materials into textiles. Kyle, would you like to answer this one?
Sure. There's a couple of different ways, primarily three different ways that all involve some combination of a polymer and the PCMs. And so one of those is you can coat the PCMs in kind of a polymer binder and then attach that to the fabric. You can also use a more water-blown polyurethane foam that has some PCMs embedded into it and sort of spray it onto the fabric, textiles, or you can laminate them with kind of a thin polymer film. Those are the main ways that people are incorporating PCMs into textiles right now.
Yeah, okay. Yeah, thanks, Kyle. And I also received another one regarding textiles, and this is about the durability of these materials or of phase change materials on textile fabrics. So this is in fact a great question, because in the presentation we covered that the main challenges today in incorporating these materials in textiles are weight reduction and flammability. But actually the third challenge would exactly be the durability, because it seems from the literature that when incorporating phase change materials in textile, the fabric handle might be compromised and the durability to abrasion actually might be lowered. But the trend is that there is definitely a trend of working on this challenge, and one of the ways, one of the ideas how this might be improved is actually by cross-linking or using cross-linking agents that connect the fiber and the shell of micro-encapsulated or coated phase change material. So we mainly mentioned micro-encapsulated phase change materials, but there was a question regarding macro-encapsulated phase change materials, and if you will give me a minute, I will just find it. I'm on the list of questions. Okay, I guess we can come back to that one a bit later. Another one that I can see right here now is how do you fabricate solid-solid phase change materials? Veronica, would you like to answer this one?
Yeah, sure. A lot of research today actually has focused on the different methodologies in creating solid-solid PCMs. And generally, two methods have been used: physical blending and chemical blending. In physical blending, a PCM, generally a solid liquid PCM, is dispersed into a polymeric matrix. The polymer acts as a supporting material and holds the PCM during phase change to keep it solid. And in chemical blending, PCM moieties can be chemically bounded to its supporting polymeric material. So these are the major ways of fabrication.
Okay, thanks. Thanks, Veronica. And yeah, going back to the macro PCMs question that I mentioned earlier, so it is about if these type of phase change materials can be used for other kinds of energy storage. Kyle, what do you think?
Oh, definitely. You know, we talked about some of the examples in the presentation, but just to give you one example of something that's a little more out in the research stage right now, there's experiments underway to use phase change materials with compressed air energy storage. So when you have excess energy generation, such as from renewable energy, you can use that excess energy to compress air, and then you release the compressed air later, such as in the evening, when you need that excess energy on your grid. Now, the problem is that the air gets very hot when you compress it. And so researchers are looking at PCMs to store that excess heat.
Okay, yeah, that's great to hear. So another question was also about what technologies will be the most disruptive in the years to come, based on our research on compiling this report. Veronica, what do you think about this?
Sure, I can share my 2 cents about this field. The application of PCMs, I think the most disruptive one might be the development of memory chips. I know that working prototypes of PCM chips have been actively researched and tested by companies like IBM and Samsung and even others. According to its proponents, and including me here, the PCM technology have the potential to provide inexpensive, high-speed, and high-volume storage in an unprecedented scale. So thereby probably becoming an industry disruptor in the years to come. So that's just my opinion.
Okay, great. Thanks, Veronica. Yeah, actually, I had the same impression as you did as well. Okay, and another question was, when can we expect to see the first prototype in barcoding? Kyle, what do you think?
Well, I'd say we're already starting to see them. I mean, the prototypes are out there. I think the question is, when will we see commercial applications? And my best guess is in the next few years. Now, this is a little bit tricky because many of the applications are in sensitive industries like money printing, police, security, anti-counterfeiting operations. And so in these industries, there's a lot of care that has to be taken to test and validate the PCMs to make sure that they can provide the barcoding or the anti-counterfeiting techniques that they claim, and that they can be used in a wide range of scenarios, and that we can trust them. So that necessarily slows down the process of getting them onto the market, but it's certainly something that I think we'll start to see in the commercial space in the next few years, even if for some applications it takes a bit longer to commercialize them.
Okay, great. Thanks, Kyle. And now I saw that we have a couple of questions regarding cost. And maybe we can start with the first, the general one. What is actually the cost of PCMs in general? Kyle, would you like to take this one as well?
Sure. It's hard to give an overall sense of cost for PCMs because the applications are just so diverse, and so the costs are going to vary quite a bit from application to application. But certainly we can say that cost reduction is one of the many benefits of PCMs. So as we saw in the presentation with the Embrace, the cost is just $25, and that is significantly less, as we said, less than 1% of the cost in the thousands or tens of thousands of dollars that a traditional incubator costs. So it's hard to get that overall answer, but I think the general answer is that at least for some applications, it's going to be significantly less than what's in the market today.
Okay, thanks, Kyle. And I noticed one other question regarding cost and micro-encapsulation. That's right. How much cost is added to PCMs in encapsulation? So I guess this would really depend on the encapsulation used. So one example that we came across is a new example of kind of encapsulating the salts. And this one adds around 5 to 10% of cost. But regarding the performance that it eventually offers, it seems to be a good trade-off. And then there was another question regarding why is Europe #1 market for PCMs? Carl, would you like to take this one as well?
Sure. So there's a couple of reasons. One is that it is simply a large and diverse economy. So it's a major market for a lot of things. Part of this is also that there is strong environmental regulation, and that environmental regulation in Europe is driving this innovation for things that can handle heat changes and heat storage in a more efficient manner. And then part of it is the strong research and development industry and culture there. So it's really a combination of factors that is helping to propel Europe to being, at least right now, the #1 market, though of course North America and Asia Pacific are also very significant markets for PCMs as well.
Okay, yeah, that's right, Kyle. So there was one other question going back to encapsulations and what are the suppliers? They're actually suppliers both for microencapsulated and macroencapsulated PCMs, and some that actually provide both, for instance, Terrator, then Schweller, the one that is based in Switzerland, and Microtact, and as well PCM products. Microtact and PCM products, they offer as well macro encapsulated PCMs. Okay, another question. What is in the report that was not included today? Veronica, would you like to say more about that?
Yeah, sure. The report actually provides more analysis of every sections that we have walked you through today. You will see more examples of the cutting-edge research and technologies application in this area, and including all the references you might need for a deeper dive. It would be a great starting point if you're working in this area or you just consider heading into the phase change material industry.
Great. Thanks, Veronica. Okay, so going back to solid phase change materials, there was a question regarding these ones versus micro encapsulated ones. So far, based on our research, it seems that definitely the micro encapsulated ones are better developed and they do have a better heat storage capacity. Solid ones, this is still relatively in development, so we hope to see some advancements in the years to come. Okay, so there was another question about phase change materials and how long they can manage the heat from batteries and what are the limiting factors here. Kyle, would you say more about this one?
Sure. A little bit difficult to answer because, again, it kind of varies depending on the industry or how you're managing it. So I don't know if I can give an overall answer of how long how long it's lasting. But I think limiting factors right now are one, looking for other matrices other than graphite for some applications. So the graphite PCM matrix works for some applications, but it's not able to regulate the heat flow quite well enough in some cases, including in some vehicle application. So that's one challenge. As I mentioned, the extra weight of the PCMs and the PCM matrix is also a challenge in vehicle situations in particular. So trying to find ways of providing enough PCMs to manage the thermal energy, but not add so many PCMs that it's adding too much weight and so much of a dense matrix. Those are, I think, some challenges. And then part of it also is just the space constraints within vehicles. So making sure that you can fit the matrix and the PCMs in such a way that they work with everything else that you need to fit into a vehicle. Those are, I think, some of the challenges right now. As we see them integrated further and in further testing, there may be additional challenges as we move to more advanced storage, and especially as we start to rely on them for, as I mentioned in the presentation, potentially sort of protection against crashes or damage to the batteries. That's not something that's been fully tested yet either. And so making sure that if we're going to rely on that matrix to provide a protection against the batteries in an accident, that we are confident that they'll be able to provide that protection in a wide variety of crash situations.
Okay, great. Thanks a lot, Kyle, for elaborating on this one. So another question that arrived was regarding the shape memory alloys, and the nitinol is probably the best known one, and if there are many others. In the report, actually, where we investigated shape memory alloys, we give kind of a list of main families of shape memory alloys, and there are more. They're mainly based on alloys, and they can include silver, cadmium, nickel, aluminium, copper, iron, platinum as well, and actually combinations of those metals that I just mentioned. The other question was if there are any shape memory alloys that are triggered by non-thermal events like electric charge or magnetic. We didn't investigate that in particular. It seems that they can be definitely triggered by mechanical force, but yeah, possibly by the other two as well. Let me see, we're coming towards the end of the presentation for today, and I hope we will be able to answer all questions, but I don't think so because there were quite so many. I think there was also one interesting question regarding examples where liquid gas change was used in phase change materials. So mainly today we were commenting about a solid liquid phase change, and we were also talking something about solid phase change materials. And this one we didn't mention in particular because actually to our knowledge nothing is available commercially, and in generally these types of PCMs, they do have the advantage of really large changes of volume as they change phase, and therefore they're not very easy to control and actually use. However, according to one of the manufacturers of phase change materials, we have seen that a type of molecules of clatterhates have been suggested as a potential group of phase change materials in the future. So these are type of molecules that are kind of host molecules, and they trap a different molecule within its case structure, and this molecule that is trapped in certain cases can be a gas hydride, and it can be actually trapped. The host can be water, and the gas can be, for instance, like methane or some other refrigerant gas. And this kind of molecules, they are able to store large amounts of heat when they melt, and they seem to might be attractive for some future energy storage applications. Unfortunately, these molecules can only be produced under a very large pressure, and once the molecule is melted, the two species cannot really easily kind of be reincorporated back. So the other advantage is that therefore they can be only used once as a phase change material. Okay, with this, I would like to close today's webinar, And once more, I really hope that you enjoyed the presentation today, and I also hope that it inspired some ideas on how you can leverage and use these really fascinating materials. Once more, thank you very much for your time, and I wish you a wonderful rest of your day.